Bismillahirrahmanirrahim. It's my pleasure today to present my department work, development of robotic and tactile sensing system for minimally invasive surgery. Actually, this work belongs to me and also my department, Mechatronics and Robotics department at Egypt Japan University of Science and Technology. Our motivation of this work in some application, such as minimally invasive surgery, in such a surgery is done through some hole, and the hand of the surgeon is outside the abdominal wall of the patient. This is to avoid the open wound or open surgery and replace it by a small incision for reducing trauma and increasing or reducing the healing time. The problem of such surgery is that the tool itself is a piece of steel. So the surgeon cannot feel inside the abdominal wall. So we think to have such system, to put some instrument and with a tactile sensor, and we can sense softness of the tissue and transfer this signal to some kind of tactile display. My department is developing tactile sensor and tactile display and also the robotic system. So my outline is divided as development of robotic system, which is here, development of the tactile sensing system, consists of tactile sensor and tactile display. Our lab, biomechatronic system, developed such teleoperation system. Usually, minimally invasive surgery consists of a master manipulator or a master robot is controlled by a surgeon and slave unit inside the abdominal wall of the patient. And the surgeon can see inside the abdominal wall by some kind of camera and display unit here. And the most famous device, maybe the only device, is the Vinci. Here you can observe the master unit, and the slave unit is here, is dealing with the patient, inside the patient, and the monitor system is here. One of the big problems in such system is that the driving mechanism is consist of wire. All this expensive device is driven by wire. After 5 times or 10 times, this wire is subjected to fracture. Okay? So we developed a new robotic system. First of all, we have to imitate the motion of hand. So this robot can do 6 degrees of freedom of hand like this. And our robot is consist of 4 arms. This is a 2 and this is another 2. This is the kinematic structure of the robot. And we, of course, we did a lot of calculation, and finally we do some simulation work. Some simulation work to find the bending angle here. Okay. And here is the end product of the manipulator. You can see here, this manipulator can do angle like 90 degrees. The manipulator is very small. This size is 1 centimeter to be able to go through the minimal invasive work. The length is about here 5 centimeters, but maybe extend to 11 centimeters. And here is our student Khalid, and here is the robot, and here is the master unit. You can operate this robot by any kind of joystick. Very cheap, very kind of joystick can operate this robot. And the workspace of the robot is very huge. Can cover 22 centimeter by around 30 centimeter. Very big working space. And here is some movie. I hope it works this time. As you see here, there is no wire. The robot is very rigid, and the operation is by linear motor outside the abdominal wall. Here, you can consider abdominal wall is here. The robot can bend freely and can cover a very large workspace. And of course, still a prototype, and you can fix the tool here. Still, we are developing the tool. But I will not show it today. So, a very nice result of this robot, it is have 6 degrees of freedom, a big working space. The control is easy and cheap. Maybe $10,000 you can make such memory. And also, the control or master unit is very cheap by any joystick. Second thing, tactile sensing system. Tactile sensing system may be strange to us. Tactile sensing system like vision system. In a vision system, you have sensor, which is a camera, and you have a display, which is monitor. And in sound system, you have a mic, and you have a display like speaker. In tactile sensing system, you have a sensor, a tactile sensor, and tactile display unit. So by this system, you can transfer the touch inside the abdominal wall to the surgery. What's done in here, the soft tissue of the patient, you can consider it like a spring. If you apply a force and measure displacement to the tissue, you can find the stiffness by this simple relation. The problem of this is that to do such a measurement, you have to put some kind of reference frame inside the abdominal wall, which is impossible. So our trick is to make 2 sensors in one sensor, like 2 springs can feel the stiffness of soft tissue. Here is the soft tissue. And by measuring these 2 forces instead of force and displacement, you can detect the stiffness of soft tissue. This is our trick in our sensor. And we designed a sensor with 2 springs, and here is the sensitive unit. I will not go in this detail. This is a mechanical structure, and this is electrical unit. And actually the size is about 4 micrometers, the size of this sensitive part. And we already fabricate the sensor with 5 millimeter, with 6 millimeter. The fabrication process is very sophisticated. It consists of silicon and thermal oxidation, ion implantation, aluminum metallization, isotropic etching, deep reactive ion etching, very sophisticated process. And we already made some simulation with the soft tissue here, and here is the sensor, and we find the reading of the sensor is very stable. If you push inside the tissue, the reading is very stable. You can observe here is soft tissue, here is medium, hard, harder, and hardness. So you can detect the hardness of the tissue. And we examine it with some kind of silicone rubber, and here is our sensor, and here is electronics. And with silicone rubber, also the reading is stable and can differentiate between soft silicone and hard silicone. And we examine it also with heart and the leg of a chicken, and can differentiate between the hardness of leg of chicken and heart of chicken. The last topic, I speak about the tactile display. This device is displaying the touch. Displaying the touch by showing displacement of this pin And also we can control the hardness of this spring. Actually, controlling the hardness of a spring is very difficult because the Young's modulus of a spring is constant. You can change it. But this kind of alloy, called shape memory alloy, by applying a current to this alloy, the stiffness changes 3 times. So you can display normal tissue and disease tissue, which is harder tissue. Okay? So by this device, if you have a lever with some abscess here, so you can display the shape of the lever, and those pins you can make harder. If you palpate it, you will feel hard. And of course, in our procedure, we have to do some simulation to test this device. And actually, this device we succeed to make only one unit, only one pixel. In the future, we will extend it to, for example, array with 10 by 10 to make a whole device. But we still a starting point for this device. And here is the operation principle. By controlling 2 shape memory alloy spring by applying current, you can control the elongation of this pin, and also you can control the stiffness. And here is our result. You can control the height. You can follow the height and control it very precisely. And also you can ask this device to make any stiffness, display any stiffness. For example, here is 35 to 100. So you can X and 3X display stiffness. Our work is published at National Instrument Company, one of the most famous companies in the world, about tactile, multimodal tactile display device, because we display shape and stiffness, so it's multimodal. Finally, conclusion concerning surgery robot. We have designed, simulate, and fabricate 4 degree of freedom robot. It can, actually it's 4 independent and can reach 6 degrees of freedom, but 4 independent degrees of freedom. The robot can actually actuated by linear motor. The workspace is about 22 centimeter by 30 centimeter. The tactile sensor, we design, fabricate, and test the tactile sensor for compliance detection. The fabrication is done by MEMS technology, and we test chicken heart, liver, and leg. Concerning the tactile display, we also did design, simulation, and fabrication for 1 pixel. And by this device, the shape and stiffness of this tissue can be controlled and displayed. Finally, I would like to thank you, and I should thank my teacher and also thank my student who implement this work. Engineer Khalil, he worked with the surgery robot. Engineer Nader worked with tactile display, and I have a lot of students in many other directions. Thank you very much.